Hi, I'm Robin. I'm at Ventana Micro. This is Jeff. You might know him. And today we're going to talk about RISC-V Vector 101. So I must admit I had a pretty hard time deciding what should go into this talk and what should not. But we'll just improvise, I guess. So the subtitle, as you could already see, is what ChatGPT told me to use. And I used it because I liked it pretty much. So, and now let's get going. So first, a bit of an overview. What is RISC-V Vector? It has been around for a while by now, so since November 2021, and even RISC-V support has come a long way. So the intrinsic support started in GC 13, AutoVec started working in 14, we stabilized and optimized it in 15, and by now it's working pretty well, but obviously there's still gaps and things to continue to work on. But also the vector spec itself is a moving target. There are several working groups that identify gaps, derive an enhancement, and so on. Vector Bitman and Vector Crypto are just some examples that are already there, and there's ongoing work, obviously.
Sad instruction.
A sad instruction. We'll get to that. In general, the architecture is vector length agnostic, just like AR64's SVE. We have 32 general vector registers, and one register can, according to the spec, actually go up to 64K bits. In GCC, we only support 4K for now, but I guess that's enough. The whole spec is targeted at low level up to very high-end HPC nodes, and that also explains some of the design decisions in the thing, which might seem odd in isolation, but make at least some kind of sense, like from the embedded point of view. So what vector operations do we have? There are no real surprises. We have like add, subtract, XOR, all binary operators that you need. We have FMA. There are vector comparisons that are called VMS, like it's meant to say vector mask set, less than, equal, and so on. We have reductions. We have mask operations. We have permutes that are actually called gather. They take one source operand and one permute operand. And then we also have lots of different other permute operations, like a slide down, a slide up, a compress, and so on, but we don't need to go into detail. Then there's also a bit of a special thing that our vector spec has, saturating arithmetic, namely like addition, subtraction, and shift. These are called vector saturating add, no surprise there. Okay, let's continue. What kind of loads and stores do we have? Also no surprises there at first. So our loads are called VLE and the element width then. So it's 8, 16, 32, and 64, hopefully, for most of the implementations. Same for the source. And we also have strided loads. That's a bit of a specialty for us because I'm not aware of any other architecture that has explicit strided loads. Everybody else encodes them into like gathers or indexed loads. We also have indexed loads. As you can see, they're called vector load unordered index with the element index size then. And we have segmented loads. These correspond to the load lane Gimple construct in GCC. And they are called vector load segment of the size and then the element size as well. What we also have, just like SVE, is fault-only first loads that load up to the next fault, where the fault would happen, then stop and continue. And of course, we have several combinations of what I already mentioned, like segmented and strided loads, segmented and indexed loads, segmented and first-only fault loads, and so on and so on. We don't need to go into detail, but there's a lot of variety there.
Is it safe to say that the more complex ones on that last bullet are exceedingly more difficult to use?
Very safe to say. So, I mean, not even fault-only first loads are, as of yet, supported by the auto-vectorizer. There's work ongoing by Tamar et al. But right now, we cannot even emit them naturally from auto-vec.
It's all done through unspecs.
Yeah, right. Okay, what you might have noticed at first, most operations don't have an explicit element size. Like an add is just an add. And the trick here is element size as well as the length that we actually operate on is encoded in a vector type. And this vector type is somehow implicit, explicit, but it's explicitly set by an instruction called vsetvl. And vsetvl, as here in this example can see, this vsetvl 0, 16, E8 sets the vector length to 16 elements. So we want to process 16 8-bit elements up until the next vsetvl is being called. So every vector instruction between this vsetvl and the next one is going to use this particular vector type. As you can imagine, placing those vsetvls is a very difficult task because obviously we don't just want to emit a vsetvl before every individual instruction. And that's what Jeff is going to talk about in the later stage of this talk, how we're going to do this efficiently or in a nice way.
Less inefficiently?
Maybe that's a better way to put it. So kind of a small recap. Almost every instruction, there are exceptions, but almost every instruction is implicitly length masked. You don't see the length just in the vsetvl, and potentially explicitly element masked. We get to that in a second, but RISC-V is the only GCC target with 2 individual masks. So there's length masking. Some IBM architectures have that. There's element masking, like AR64 does it, but we have, I'm not sure I should say the best of both worlds, but something like that. We can ask it later, yeah. We'll ask it later. So I have 3 or 4 of these recap slides. I'm not going to read that out. It's just in case anything has been unclear. So any questions or so for now, we can answer them right away. If not, we'll continue. So that's just a short recap of the previous. It doesn't seem to be the case. Then let's continue. So this is a first concept slide. Length masking, what is it about? So there's like my pointer cursor on the way. First, again, we set the vector type to 8-bit elements, and we set our length to 16. For the first instruction that we're going to process, this is a broadcast, and this vmv.v.i broadcasts 0 to the vector register 4. So we just broadcast 0 at a length of 16 8-bit elements. That's pretty simple. What we're going to do next is set the vector length to 15. And then we have a thing called mask policy, because for a length of 15, you have a tail. So one element is not processed at the end. That's our tail. So we have a mask policy for that tail, how it's going to be handled. The TU here specifies tail undisturbed, meaning the old value should be preserved. So if we do another broadcast with length 15 now, and we broadcast 3, our vector should look like 15 3s and 1 0. So the 16th element just keeps its old value. We also have another policy there that's called tail agnostic. So we do the same thing. We broadcast 15 elements, again to V4, but the 16th element now is in the tail, and the policy is tail agnostic. So what you would usually assume is that the value stays the same, but now the microarchitecture has the choice to do not really whatever it wants, but it can set it to -1, it can keep the old value, whatever it deems more efficient. And we'll get to that later, why this poses a problem. Before that, let's look at element masking. It's pretty similar, actually. So again, we start with a 16-element 8-bit vector. But for element masking, we need to define a mask. And masks are always specified, if we want to make use of them, in vector register 0. So for that case, we set the mask to 1, where V2 and V3 are equal. Vector mask set. Next, we unconditionally set 16 elements of the V4 to 0 again. And now again, the same game with mask policy. There's also, it said here, yeah, right. It says mask undisturbed, meaning we want to keep the old value. But as I said before, element masking is always explicit. So once we use element masking, we need to specify this v0.t at the end. This makes it explicit that element masking is taking place. So we set v4 to 3, where the mask is true, and the rest of the element stays the same. Same game with mask agnostic policy, just that the values where the mask is false can be anything. So that's the general concept of those two masking types in RVV. How does this look like on a GIMPL level? So regular operation masking in the vectorizer is done by internal functions. So that has been present since, I think, Sandiford introduced this to AH64 a while back, 2018 or something. We use internal functions that they are basically a black box saying, we're doing something here with masking, and we have a condition, we have an else operand, and that just encompasses what a conditional operation or a masked operation does. For us, as we have two masks, we needed to introduce a length variant of all the existing conditional internal functions in the vectorizer, because the length must be present here as well. Then there's a little trick that Sandiford did back then. We don't want to reinvent all our match-PD patterns for these internal functions, obviously. We want to make use of what's there. So the trick is to kind of remember what the mask is, what the else is, but strip everything else up to the underlying operation. Here it's an add of operand 0 plus 0, which is obviously no add. So we can condense that to operand 0 and then add all the boilerplate back that we saved before. So that's how optimizing those internal function works. Usually what we did before was just create a vcon mask that's basically a blend or a merge out of this. But for RVV, that's not sufficient because we have the length, obviously. So we needed to also invent a vcon mask length that's a blend or a merge with length. This is only relevant for RISC-V, but we needed it especially for this kind of optimization. And without that, we'd be pretty helpless on a match-PD level.
And one of the key goals here is we want to reuse as much infrastructure as possible.
Definitely, yeah. Otherwise, those internal functions just remain unoptimized, and you really want to optimize away an addition with 0.
Right. So. And when you go down to RTL, the RTL, if you fully expanded this stuff, would be much more complex than the RTL optimizers know how to.
Yes, that's one slide later, in 5 or 10 slides or so. No, go ahead. So now is where the issues start. This one was, so far it has been pretty simple, but what about loads? A load looked like this, a mask len load. I mean, the len wasn't there, but the length addition is trivial. So it was called mask load. It had a source, it had a mask, and now it has a length, but there is no else operand. And GCC's assumption was load always zeros mask inactive elements. So that's how AH64 handles it, and that's probably the assumption. But, well, we don't. As I said before, depending on the tail and mask policies, the value can be anything. Not really anything, but it depends on the UART, we cannot say in advance. So, there's even, so some choice is to not zero out the elements, but -1 the elements, fill it with -1s. It's also not very complicated, but the rationale in the spec explicitly spelled out is so people don't rely on 0. GCC relied on 0. So what we needed to do is amend the vectorizer by a specific, let's call it predicate here, and these are defined in the individual backends. It's a mask load else operand, basically specifying what the target is able to handle. The first one is ours. A scratch operand is basically a GIMPL speak for I don't know. And the AH64 one should stay as before. It's just a 0. It will only accept 0 constants for that. Then how is it going to look like in the vectorizer before? So the vectorizer will query the target, what can you support, and then decide its strategy from there. So before it just was a mask len load, do anything with it and continue with your operation. Now it's basically we load into temporary if needed, not all the time, it's just very rare that we need it, but sometimes we do. Load into temporary, load a 0 if we need a 0 for some subsequent operation, and then merge according to the current mask with this 0 element, with this 0 vector. That's how we do it now. And that wasn't present before and led us to some nasty bugs in the vectorizer.
So you spent a fair amount of time chasing these down.
Yes.
Is that vectorizer, or is that RISC-V code?
Which one?
This stuff you said before or after, the after.
I mean, that's GIMPL, how the vectorizer emits it.
Okay.
So it's not in the backend code. Yes, but like their advantage is they can rely on the zero. So the vectorizer only relies on zero, and we're the only backend that doesn't provide that. So this like temporary code will only be generated for us. So, but yeah, it's generic, not generic, but generic in the vectorizer.
Somebody else could have a similar architecture one day.
Yeah. Okay, let's quick time check. Okay. Concepts, again, how do loops look like ideally for RISC-V? And now we get to a second usage of vsetvl. Before I said vsetvl sets the vector length and the vector type, but it can actually do a bit more, which is pretty nice in my opinion. So suppose we have an array size or length stored in A5, in the register A5. And obviously, being a VLA architecture, one core will be able to operate on 8 elements, the other on 16, 32. And vsetvl knows that, kind of. Obviously, it knows it's what it's currently running on, looks at A5, the array size, and then decides which chunk of the array to process. So on a large architecture, there might not be even a loop, but we'll just run through it once. On a small architecture, we might loop here. So that's what vsetvl actually does, stores the current target's preferred, I say preferred here because there's intricacies, preferred vector length in A4, and then just operates on that for the subsequent operations. That's pretty neat, actually. So you can just branch on A4, and if you're done, you're done. If not, just continue. And that's how we do it.
Was that add supposed to be a sub for your loop count?
Yes, probably. Very much, very likely. Yes, yes. I mean, a bump is usually upwards, right? But it should be. Zero. Definitely. Yeah. Okay. So the whole thing is called length-controlled loop in the vectorizer, because actually only loads and stores are length controlled, and all the operations in between, like an add or something, run at full length. That's how all the other targets also do it, in particular S390 and Power. They use this length control, but AH64 has a similar thing. They just don't have the length, but they encode their length in their mask. So it's basically the same thing. So that's one takeaway. Like just the loads and the stores are basically length controlled. The rest is full size. With exceptions, of course, but that's how it usually looks like. So and in general, that's how a nice RISC-V loop looks like under certain conditions. How does it look like in GIMPL? I said other architectures also have this, like S390 and Power. They use a set or a number of minimum and maximum operations to determine how much processing, how many elements are left to process. We have vsetvl, and obviously we need some kind of way to let GIMPL and the vectorizer know how to use vsetvl. And this idiom or construction is called selectvl in GIMPL. We also needed to introduce this because the other length control targets are fixed length always, and not VLA, so they know how much to subtract in each operation, in each loop iteration. So for us, it's unknown, and this is what selectvl is supposed to encompass. So under certain preconditions, like if the loop counter is downwards counting, again, then we go for selectvl. We have some cases that we could use selectvl, but don't right now. But so far it's working well enough, and that's like very low on our priority list to improve there. So most loops work well with the current scheme. So jumping to another topic, I talked about masks. RVV vector masks are different. I'm not saying difficult, but they're different because we don't have padding bytes in between the elements, but we just like lump them all together at the beginning. So it's just 1011 or so, and the padding bytes are at the end. AH64 pads differently between the elements, and GCC was only prepared to handle this other scheme, so to say.
A sparse scheme.
Yeah.
And that is, interesting from the hardware guys. I've been told in the past that these packed schemes are actually fairly expensive to implement in hardware. So, well, I guess it's just hard on the hardware guys.
Yeah. I mean, we have different issues to tackle here. For example, there are several cases, like in all of the middle end, where we use get mode bit size of a mask. But that's 8, because the bit size is the whole byte. We need to use get mode precision, which is 4 for this particular mask. And there were like at least 10, 15, 20 cases that we needed to find. And as you can imagine, those also turned into subtle, nasty bugs when not found.
Out of curiosity, Robin, has this problem popped up once they were fixed the first time? Are they being reintroduced, or are we pretty clean on this?
No, we're clean now. The last one that popped up was this var-asm encoding scheme, like half a year, like
so
3/4 of a year.
It's not a recurring problem.
No, it's not recurring. I think it's fixed now. So it's not like rampant, but there are limited islands in the middle end that make heavy use of it, and those are fixed. Should be fixed now. And yeah, there's the var-asm example I just see.
But uses of this in like the middle end, where it's architecture independent, that we have to worry about?
For like new patches coming in from
What
ARCH64?
I was starting to touch on was, is this being reintroduced by accident?
I don't think, like, as long as you're not touching any mask handling, which is unlikely, it's not very likely to reappear. I think it's just the general handling that's fixed now, and that should just work. I mean, fingers crossed, of course. I mean, okay, another thing. So this is just like, as I said, it's a bit of a collection of things we encountered. Vector load store alignment. That's a funny thing because like we explicitly spell out in the spec, in the RVV spec, that element misalignment of vectors may cause a trap or an exception. So cores may basically give up. Meaning we need, like right now, we need to default to no unaligned support for vectors in GCC, which is a very poor choice for all but low-end architectures. But here we are. So far, our default is no unaligned vectors. And we introduced like a switch, mno vector strict align, that allows to still generate those.
But at least on power, our vector size was 128 bits.
Yeah.
Our loads had to be basically, for some of the older cores, 128-bit aligned, but this is element.
This is element misalignment,
so,
yes. The other one is not spelled out.
So for a, 8-element vector of whatever size, it only has to be
like
aligned on
the one byte
part?
Element size. Yes, that's
okay.
it. That's it.
Okay, so that's not that bad, right?
It's not that bad.
Well, it happens still. I mean,
okay.
If you're playing tricks in the vectorizer, just reinterpreting like 4 bytes as an int or so, you're already bitten, because it might be byte aligned but not int aligned or something, and this happens.
Or you just think a sad loop.
Yes. Yeah.
Everything's going to go back to a sad
That's a prime example. X264 sad loop where you try to unroll, and you have byte accesses, and those just become unaligned then. So, yeah, well. So, I mean, luckily, as you said, it's not that bad. But on top, the vectorizer wasn't even prepared to check element misalignment for gather, scatter, or strided loads. And as we have those, obviously we need to be correct on that. A patch has landed now, like, I don't know, was it a month ago or so, that fixed that. But before, I mean, we could be wrong in 2 ways, right? Either by not checking or by, like, ignoring it. But for now, this should also be fixed. And there's also work to ameliorate the situation. There's RISC-V profiles now that mandate that misaligned access should be supported. It can be slow, I guess, but you should not fault. So in the future, we should be better off. But for now, well, yeah, that's the status. So again, some kind of recap slide, but I think every question has already been asked.
Questions right now?
But you can tell the compiler that, like, trust me, this is the VLAN, right? So the
You mean as a general compilation option in
Yeah,
MArch?
that
Yeah,
it's
we'll get
fixed.
to that. We'll get to
Okay.
that. Okay. Yeah. You mean just fix a vector size if you know this is what I'm running on? Yes, yes, that's possible. Okay, another controversial topic. ELML is a concept that, to my knowledge, no other architecture has. Other architectures have like register pairs or something. We have register pairs. And what's the other term? Quads and octs. Octs, yeah. So, well, yeah. So as an example, we load 16 8-bit elements, and then consecutively in memory, we load the second 16-byte element, 16 8-byte element vector. We could also express this as load 32 8-bit, not byte, 8-bit elements with an ELML of M2, lumping just the two vectors together and then operating on a larger vector. Those vectors then are register pairs. In that example, it would be V4 and V5. That would always come together. This obviously has performance implications, but I'm not going to go into this now. We can discuss offline.
We can spend an hour on the performance.
At least, yeah. So I guess the current status is that all North American vendors tend to go to ELML 1, and the rest varies. So we just talked to Keto before, and their cores almost always prefer higher ELMLs, up to 4, maybe not 8, but 4. So there's different trade-offs here, but that's very much a microarchitectural discussion. One other way to imagine ELML is implicit loop unrolling. So if you have a large loop, you can imagine that when just increasing your vector size, you can fit the whole loop into one ELML whatever vector, and you wouldn't need to do any branching overhead or something, but just operate on one big block. So that was also one of the other rationales for ELML. Get rid of the loop entirely and just operate on the vector. So.
And one more note about ELML before you go on, Robin.
Sure.
Think about what happens when you have an ELML 8, which only have 32 registers. You start to become a lot more likely to spill.
Yeah.
Nothing good happens when you spill.
Exactly. So that's also spelled out here.
Oh.
ELML, feel free. So ELML 8 will leave us with 32 divided by 8, meaning 4 registers or register octs, basically. So what are you going to do with 4 registers? Not a lot. If you need to load 2 values, you can just add and store. That's it. But for more complicated loops, you're going to have difficulties.
Can you set this elbow inside the function? So this elbow, is it set for everything?
That's set
front, or
up to your next vsetvl. That's part of the vector type. You set it for a block inside
so
the function.
The compiler can choose to reduce the elbow to
We're
improve
doing
the
that.
register
Just
location.
wait for some slides. We're doing that.
Okay.
You absolutely can. It's totally dynamic.
Yeah, if you want it to be. Okay, so as like an internal node, we specify this alignment of a mode via some additional function and enforce it in hard regno mode OK. So if a mode hits hard regno mode OK, this is like a hook, and we see the actual register doesn't match the alignment that ELML needs, we disagree and just say no, give me another one. There's also fractional ELML, so not only can we increase the vector size, but we can also reduce it to 1/2, 1/4, 1/8. And these, luckily, at least don't have register constraints or restrictions. It always fits into one, like, not fully used register then. And this gets us to a typical use of ELML, extensions or conversions. V0 extend, for example, VZX, VF2, 0 extends a vector register. And as you can imagine, if you increase the size of the elements, something must happen to your vector size somehow. And this is a slide about that one. How do we do that? All our conversions are, I call it VLA style, that's not a proper term, but we keep the number of elements the same, while in VLS, we usually have unpack one lower half, and the vector size stays the same. But you need two vectors then. So that's the difference. We try to keep the element number fixed across the conversions, and unpack low and high don't, basically. I mean, it's still the same concept, of course. They're related. What you could also say is we only have unpack low instructions and only always unpack the lower half. So the question now is, if you have a full vector of, let's say, 8-bit elements, what are you going to do? Are you going to allow larger vectors if you zero extend? That would be an Elmore 2 then, if you have a full vector. Or are you not allowing the full vector of 8-bit elements in the first place, but only a half one? So that's a crucial design choice, what to do. We're not really sure about it yet, but right now, the largest type in a loop, let's say if we extend from a character to a short, will determine the maximum vector size. So if we extend the 8-bit elements to 16, only the 16-bit elements will span the whole vector, and the other ones will be smaller. So that's our current design choice. As I said, there are performance implications with Elmo. We're not going there now. Let's talk offline about it. But that's our current implementation with Elmo 1 default. So a bit of a short excursion to how our VLA modes are called. They always have this RVV prefix, then the Elmo, usually 1, and then the scalar mode. So there's no big surprises there. RVV M1 QI is a full vector of QI modes for the current architecture, but it obviously translates. So it's 128-bit on a 128-bit implementation and more. So these have a bit of a double meaning. Our default march is, I'm calling it default for now, it's RV64 GCV has 128-bit chunks. So it starts the minimum vector length that you mentioned before is for our default is 128-bit, and everything else is relative to that. And this is similar to AH64 specified in a poly-int in all of the target independent passes, meaning we have one chunk on a 128-bit architecture. If we compile with the same option and run on a 256-bit, it's obviously double the size, but still the minimum length is 128. So this is what we can rely on, and we cannot rely for this option on 256. And then a bit of detail how this poly stuff is calculated. I don't think it's that interesting, but the poly is actually a polynomial thing. The first one is the static offset that you always have. This is the 16 bytes. And the next one scales by the vector length that your current running target has. So it's either 16 plus 16 times 1, times 2, times 4, and so on, that gets you the proper vector size in the end, like the runtime vector size. And as I said before, such binaries compiled with the default option will run properly on our microarchitectures with larger or equal or larger than 128-bit vectors. So that's how it works. If we want to go higher, as to your question, we would specify a ZVL 256-bit, meaning we generate code for everything 256 and larger. This allows you more refined optimizations, and obviously more higher performant code usually. Question there?
Still not a VLS.
Yes.
Yeah, well, my question, or what I was going to ask, is that you can also specify, these days you can also specify, now you specify minimum length, now you can also specify exactly it's going to be this amount of bits.
Yeah.
Does that influence the decisions that the vectorizer makes? So
of course, yes.
So it doesn't need to do like the get the VL.
No, then
So
yes.
it can do like neon style vectorization.
Yes, that's what we also support.
Yeah.
It's not a real first-class citizen. There's some bugs there still. So right now, if you specify a fixed vector length, at some point it will generate worse code than with this option. There are known bugs there that we just have to fix. But ideally, yes, the code with a fixed vector length is always better because you can have better assumptions. So that's how it works.
Thank you.
However, the general consensus has been that most folks want a VLA style so it can scale up as design scale up.
Yeah.
But the thought all along, I think, has been that at least for benchmarking and certain codes that a VLS style would be more appropriate, particularly in the benchmarking space.
Yeah. Codecs are a prime example where you usually want a BLS style.
It just doesn't perform well yet.
Yeah. Okay, so a quick note on the vector mode selection. That's like for a VLS architecture, it's pretty simple to choose a vector mode because there's only one you can choose. You have a fixed vector length, you have a type, and there's one type that fits, basically, or a mode that fits. For us, it's not that simple. So like AH64, we give the vectorizer a number of modes that could possibly work, let it vectorize, and then get back to us via a costing hook and decide which one is best. That's how it's usually done. So we start with, let's say, M1 QI, then half the size, and that's how we get to a, oh, there's a question. That's how we get to a proper vector mode.
So this looks like you have the fractional things, but
yes.
You don't have the ML2?
No, by default,
things?
the maximum LML is 1.
Okay.
Only if we specify MRVV max LML 2, 4, or 8, we go higher.
All right.
So I think that's on one of the next slides. There are not many slides left until you can take over. Yeah. So what we also offer, and that gets back to your question, is proper VLS modes. So suppose we have a minimum vector length of 128, then we allow all VLS modes up to that size because they just work. And this offers you a bit of a best of both worlds again, because up to that size, for like X264, a good example again, many loops are small and use small like element sizes, then you can just have a VLS style vectorization with all the benefits it has in the vectorizer and still vectorize other loops that need a large like vector size with the VLA approach. So this helps us a lot, especially in X264. And just like as an example, there's lots of modes we have to offer to the vectorizer. Of course, we choose wisely, but there's still a high number of modes. And this made certain changes in the emit functions necessary. Before, there was just gen emit or insen emit and so on. And the one function, at some point, we reached, I think, 30 megabytes for insen emit or more. It was insane. So it was a huge bottleneck for compilation of the compiler itself, for Bootstrap and all that. So we needed to split. We needed to tell gen emit to split all your insen emit stuff and insen recoc. I think those two were the main culprits. Yeah.
And it essentially became a huge serialization point during build.
Yeah.
Because these things would take 20, 30, 40 minutes.
Yeah, something like that. It's still slow with 10 like partitions, but it's much better now. And I think it also helps other targets.
Yes.
Okay, I think we already went through that. I'm not sure if we should still, especially looking at the time. So vector mode selection, how do we choose a vector mode? That's not particularly RISC-V specific, but it's always if the vectorizer sees a different scalar type than before, it asks the target code or the backend via hook, which vector mode do you want me to use for that? So that's the basic principle there. And again, as I specified, or as I said before, we try to keep the number of units constant for our conversions, and conversions is where it matters, because only then you have a different type in your loop. So if, for example, we want to extend from 8-bit elements, from characters to shorts, we first have chosen for example, V8 QI mode, so 8-bit elements. And what we then select in that hook is V8 HI. So again, keeping the number of units constant and not do some like SVLS architectures do, like go with 2 vectors, but we stay with 1. So that's kind of a crucial distinction. And the problem now becomes there are certain instructions, Rivos's SAD instruction is a prime example, but also the dot product, that don't conform to this, like keep the number of units constant. The SAD instruction is in itself a reduction. It reduces a number of, let's say, characters to integers. It just sums them up. And so the number of units don't stay the same. This is ongoing work. We don't have a proper solution how to like nicely implement this in this target hook, short of just offering all the other modes as well and throwing 90% away, which is not a great solution. But as I said, that's like ongoing work, and we need to figure out a good way.
And that SAD instruction, I think, is still in flight from a standardization standpoint. That's not set in stone yet.
Yeah, but the dot product is there, so we have to deal with it one way or another. And I'm afraid there will be other extensions in the future that will just go with VLS style. So this problem needs to be solved. Yeah, yeah. Okay, Elmol selection, that's, I think, one of the last slides we have for that. Default is M1, as I said before, no grouping. We can change this by max Elmol parameter, but we also have a dynamic parameter, meaning we try to choose the Elmol as high as possible as long as there are no spills. So how we do that is we go through all scalar statements, try to track the liveness of them somehow, and the number of vector registers that are currently live at this, let's call it program point. And as soon as we notice there are more live than we have, we consider it a spill, a necessary spill, and decline this Elmol choice, go one lower. So that's how it works, basically, on a high level. I just visualized this a bit, but I think it's clear enough. So we just start with Elmol 8, maximum. If it spills, 4. If it spills, 2, and stop somewhere, latest at 1, I guess. So that's how it works. So that's also back to your question. That's how we can do it. But it's not the default, because, as we said before, this is very URH dependent. Some prefer Elmol 1. Some prefer 8 or 4 or something. So we decided not to go with a default of dynamic unless we have proper data from a number of vendors, basically.
Yeah, and I think at some point that'll go into the tuning structure. Where a microarchitecture
Yes,
will say,
that
"This
should
is what I
definitely go there, definitely, yes. So nobody has to specify it by hand. So again, a recap. Somebody wants to, guess we're good. Quick about RTL. So this is the ugly mess of what we have in RTL representations. I mean, as I said, two masks, a number of vector types that are needed to be encoded. In the end, it's an if then else. So if mask, then do this, otherwise do that. This is all somehow also documented in vector.md in our backend. I just wanted to recap quickly, but basically we have a big unspec there. That's the condition of our if then else. That includes the vector length, the mask, all the tail policies, and some other needed boilerplate. And finally then the last like 3 lines or 4 are the actual operation. And as Jeff mentioned before, there's no way combine can work on this. There's no way. So what are we doing? We use define incident split. That was a big topic yesterday. I'm sorry, Jeff. But I mean, for now,
This is probably a good use.
we still want to get rid of it, I guess. But for now, we do that. So every AutoVec RISC-V vector instruction is a define incident split that is simple, well, for certain definitions of simple, that just does set, let's say binary operation, source, source. And this way, we can ensure our instructions or our representation of those is simple up to the first split. So combine can combine, forward propagation can propagate, and so on. So we get, again, of course, we don't want to reinvent the wheel. We want to reuse what's there. And that's how we achieve that.
It's the best way I can think of. So essentially, define and split in this context is target lowering. It's just a delayed lower.
Yeah, right. I mean, one way would be to introduce all of what we need, let's say a widening add or something that doesn't exist in Gimple, to the Gimple or to the vectorizer, and have internal functions there and optimize there. That's probably a long-term solution at some point, but it's a lot of work because we have a lot of instructions. So for now, we go with that route, and it works nicely.
Does SVE not have this because they're masks?
No, they just don't care that much. I mean, like honestly, not a lot is happening optimization-wise for vector operations anyway. So it's not like scalar stuff that gets shuffled around and turned into 2 into 1, and so you can get away with not.
It's a legitimate question.
Yeah.
Like, how much RTL optimization can we do?
Yeah.
Don't know right now. I wish I had that answer.
Yeah. So.
I would love to avoid that.
Yeah, everybody would like it. It's just, but yeah, that's where we are. So I have a bit of ongoing future work. I mean, the first point is what we just discussed. So move or add more internal functions that match RVV semantics so we can exploit match PD and make use of the already existing optimizations that are there. Improve the VLS only support, what we discussed, and there's just certain bugs there. The next point is like a general one, but for us it's interesting because we have a large vector unit, 512 bits. So the vectorizer right now cannot, for certain loops, cannot properly make use of large vectors, but it tends to prefer smaller ones due to certain design decisions that we don't need to discuss right now. But that's an ongoing thing that's very interesting for RISC-V vector because we will have a lot of variation vector size across the board. Next thing is also interesting because we're the only target with an explicit strided load, not an implicit one. So we need to make better use of that, make it a first-class citizen vectorizer. That also helps X264 and other benchmarks. And what's also part of that is the vectorizer right now just thinks everything is the same, which it kind of is, but it might or is probably slow or slower than scalar, which it is not, definitely. At least for our microarchitecture, it's not. It's faster than scalar. But right now, it's modeled as a series of scalar loads, basically, in the vectorizer, which is definitely not true for us. Yeah, and more topics are going to be in the RISC-V BOF.
And so
Over to you.
Safe to say that trying to get the strided load as a first-class citizen has been painful?
I mean, there are more painful things, but yes,
Yeah,
of
fair
course, everything is kind of painful.
All right.
Life is pain.
Life is pain. Wow. Well, I guess we have a new quip. I should add that to the slides for tomorrow.
Get a new subtitle.
Yeah. Let's see. I'll go over here. So vsetvls. We are probably the only architecture that does this highly dynamic vector link setup, highly dynamic masking, blah blah blah. And gosh, I think it looks like there's a slide missing. Did we skip forward? All right. Huh? I don't know. So this looks more like a conclusion slide. All right, so I guess we'll just go with it. All right, so first bullet, generally avoid speculating vsetvls. And this came out of initially one problem, but actually in the last few weeks we found a second problem with speculation. On some microarchitectures, if you speculate a vsetvl past a control dependency, which potentially would mean that vsetvl sets the link to 0, your performance craters. And I won't say whose design it is. I don't know how bad the quote-unquote crater is, but I've been told don't do this under any circumstances because it's bad. The second one we found very recently is in Perlbench. We had a case in the main Perlbench interpreter loop where you've got this nice big block of code. And on some designs, they're starting to see fetch block-based optimizers. And that big block of code goes into the fetch block optimizer and would be optimized. Unfortunately, on these fetch block-based optimizations, you have to stop fetch blocks somewhere. Or maybe you have restrictions on instructions that can go in these optimized fetch blocks. On our design, if you have a vsetvl, you can't go through the fetch block optimizer. And so what we were finding was we have the main part of the interpreter loop. It's hot. That's very hot code. You have a switch statement and then all the different cases for all the different operators. And what GCC was doing is it was speculating from the case labels, which are extremely code and never actually trigger in the benchmark and are statically predicted as highly unlikely to be taken. It pulled those vsetvls up into the hot code. And that is bad just in general. And for our microarchitecture, that's extraordinarily bad because we don't get an optimized fetch block. Not only do we not get an optimized fetch block, the path from optimized fetch blocks into the execution units is wider than our standard decoder path. So it hit us twice, and it's about 1 to 2% on Perl bench for spec. So it is meaningful. Yeah, this is the conclusion slide. I'm not sure how we got it backwards. Go forward one more. Yeah. I don't know what I did. This might have been in my hotel after being on a plane for a day, so I'm sorry. One of the basic concepts of vsetvls and RISC-V is we really think about a RISC-V vector instruction as a 64-bit instruction. There is a prefix, which is the vsetvl. You can conceptually think of every RISC-V instruction RISC-V vector instruction as having a vsetvl in front of it. And then you actually have the operation. So it's a 2-chunk instruction. But then you can eliminate the vsetvls, and we do that through a lazy code motion algorithm written by Juzi at RIV-AI, if I recall. And LCM, the concept behind LCM is to look at all the paths of the control flow graph and minimize the number of evaluations of an expression. That's where it came from. It's from the 90s. I think I did the original GCC one based on code from Doug Evans in like 1999. But we're using that same basic framework to eliminate vsetvls that have a compatible setting. Robin didn't touch on it. So a vsetvl could be an exact match, but a vsetvl that's just doing data movement, you can kind of pretend it's a different size. You can change the length and the number of elements, and you can play games there and do some cool things. We have an LCM optimizer that tracks vector state for each instruction that it needs, and we'll try to optimize away unnecessary vsetvls. We've also realized that you can eliminate duplicate vsetvls by adjusting the scheduler. So as you're emitting instructions in the first stage scheduler, you can track your current vector configuration. And so when you're preparing to issue your next instruction out of the ready queue, maybe you have 3 instructions at the front, and maybe one of them has the same configuration that you just emitted. Well, damn it, emit the one that has the same configuration because it's going to save you a vsetvl. And it doesn't always save because sometimes you have to emit another one somewhere else, but it saves reasonably often. And so the basic concept we're starting to come to is we need to track vector configuration outside of just the vsetvl insertion pass, outside of as essentially a reusable module. And so that's something we think we're going to tackle. We do think we're going to need additional microarchitectural control knobs here. In the scheduler, you might have a priority. And right now, in the code that we wrote for Ventana, we have to match the priorities exactly. And the idea here being is we don't ever want to regress CodeGen. Some architectures might not be terribly sensitive. We might say, well, if your priority is close, select the one with the same configuration, but a close priority. That's still to be determined, and quite frankly, we need real hardware from multiple designs to understand where that knob ought to be turned to. And then last but not least, we have one Bugzilla where somebody has asked that when they see a computation of the vector length in bytes times 8 to turn that into a vsetvl instruction. And you have to track the vector configuration to know if this is going to trash your current configuration or not. I've been told this helps on some designs from one company, and again, I'll just say they're nameless. But again, the point being is there's all kinds of weird things that go on the vsetvl. We're going to need a lot of architectural testing and development to understand how they all interact and what's the most important thing to do. We've been told that some microarchitectures do avoid vsetvls like the plague. Others are like, yeah, don't really care.
And then that's what the hardware guys say. And then we get in there with software and we benchmark and say, well, we do care, just not as much as some others care. So again, I think there's gonna be a lot of work in this space over the coming years as we see real hardware come into the market that we can benchmark beyond just running spec. You know, I need better hardware to be doing this kind of analysis. Yeah, touched on those because I know that slide was supposed to go earlier. You guys want to talk about register allocation of vsetvl, or are we good? What's our time, Robin?
We have like 2 to 3 minutes.
2 or 3 minutes? This is probably not that interesting. Track the vector state. Yeah, so these things are out of order. Oh, I'm sorry.
I'm sorry.
No, I'm the one that added them to your deck, so I think I actually covered everything in there, so I think we're actually good for questions. Nobody's asleep, so I will just assume you internalize as much as you wanted to. Thank you very much.